So as I was about to write up the homework solutions, I realized that I could, videotape myself recording them. I've never done anything like this before, so it's a bit of an experiment. I'm not sure how useful or interesting this will be, but I guess we'll see how it goes. Not sure exactly how long this will take. Probably less than an hour, I'd hope. And also in 20 minutes I'm going to have to leave for a meeting, so there's going to be a pause. But anyway, let's get started. So I'm writing all the homework solutions up in LaTeX. Let's see, so I'll start by indicating that this is the solutions and remove the instructions. And one thing I have set up, so at the top of my file I've got some instruction macro, or I mean a solutions macro. So let's see, I'll create that environment. Now it's not called solutions, but solution. Let's see if it works. So compiling, okay, there we go. So what is the first problem? So we've got a set of natural numbers such that 7 is less than n squared. So one question is it non-empty? And another is find its least element. So let's see. I guess there are a couple things. One is we can just find any element of it to prove the first part. So I'm not going to be clever. So no, let's say that 7. 7's an element. And that is because 7 is less than 7 squared. So S is non-empty. And one thing is, the point of this question is, this is a subset of the natural numbers and it's non-empty, so it does have a least element. And this isn't necessary to say, but I'm just pointing it out for you. Let's see. So one of the ways to check what the least element is just to go through and check whether elements are in it or not. So let's see. Let's compile it just to see where we are. So 0 is not in it. I'm really not going to be very clever about this. Let's see. Let's just go through. So 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So our claim is that 3 in S is the least element. And this is because 0, 1, and 2 are not in S, since 0 squared, 1 squared, and 2 squared are less than or equal to 7. But 7 is less than 3 squared. That's enough. Okay, let's compile. Great. Okay, so the next problem. We've got a set. Oh, let's set it up. So it really wants to create solutions instead of solution. That's annoying. Okay, so we've got the set of all 2k and the set of all 2k plus 1, and we're taking the union, and we want to show that S equals the natural numbers. And we're supposed to do that by showing that it is an inductive set. So a first thing is, let's see. We want to show it's an inductive set. So the claim is that S is an inductive set. And so there are two parts. Let's see, do I want to write it like that? Let's do the two parts. Let's just, recall that S is an inductive set if two things are true, 0's in S, and 2 for all n in S, then n plus 1 is an S. So that's the definition. So claim 1 is that 0 is an S. Okay, so by definition of union, I'm going to just do this in all the detail. So by definition of union, it suffices to show that 0 is in the set 2k for all k in n, or 0 is in the set of all 2k plus 1 where k is in n. Okay, what are these sets again? So it's the set like given well, it's I guess the image of the function of k maps to 2k and k maps to 2k plus 1. So I guess if you know what the definition is, then it's kind of clear that 0 is in the first of the two, because we can set k to 0. So since this is an OR, we can show that either of them is true. So let's show the first one, and let's copy paste. So by definition of set builder notation, this is that there exists a k in n such that 0 equals 2k. And then let's use k equals 0, and that is that. So the next claim is the second part of an inductive set. So let's expand out what it means to be an element of S. And that is, okay, so we want to show this claim, and we'll suppose that n is in S, and we will show that n plus 1 is in S. Okay, then because n is in S, then n is in, I'll just copy this. And fix the zeros, turn them into n's. Okay, so then, let's compile, see how it's doing. Ooh, that's formatted in not a nice way. Let's see, how can I fix that? Because I want this to be indented, ideally. Maybe I'll fix it later, before I post it online. Well, at least there's a new line. And I know LaTeX does let you do this, but I'd have to look it up. Oh well. Okay, so we know that n is in one of these two sets, and it suffices to show that n plus 1 is in one of these. Okay, so there are two cases. And the description environment is pretty nice for this. So case 1, I'm doing a case split on the assumption okay, so n is in that, so let k and n be such that n equals 2k, using the definition of the set notation. And then, well, we will show, well, let's see, adding 1 to both sides, we have that n plus 1 equals 2k plus 1. Hence, n plus 1 is in the second set. using, somewhat perversely, k equals k. Where this k is supposed to be the k in the definition of the set, and that k is the value that we're using. Maybe I'll make this a little clearer by choosing a different variable, in this case k prime. It's a good way to make up new variables. Okay, so using k equals k prime, where n is 2k prime. And this is the right side of the disjunction. And it suffices. Where I recall a disjunction is an or. That's the is Latin for it in English. Okay, so now the second case is n is in 2k plus 1, so let's let k prime and n be such that n equals 2k prime plus 1. And then adding 1 to both sides, we have n plus, oh, oops, that is not the right second case, is it? Too bad I don't have chat off to the side to let me know of my mistake. Okay, so let's fix that. Oh wait, what am I doing? I've forgotten. Okay, now chat was telling me that I shouldn't have fixed that. Right, okay. I just need to compile and look at what's going on. Okay, so it suffices to show that n plus 1 is in one of these sets, given that n is in one of the sets. Okay, so second case, n is in the second set, so let's let k prime be such that n is 2k prime plus 1. And, oh yeah, sorry, you might, I'm just kind of like writing the proof down, but, you know, I've thought about it a little bit already. So it's not like I really have to, like, solve it all. So I just figured that since we have even and odd sets, basically, of the natural numbers, then the induction step is that if you have an even or odd number, then when you add 1 to it, it's either odd or even. So they kind of flip roles. So we're saying that if we have some, oops, remove annotation. Okay, if we have an even number, then it will be the second set, and if we have an odd number, it'll be the first. So we had an even number, we showed it's in the second. Now we have an odd number, we'll show if we add 1, we have something in the first. So we have n plus 1 equals 2k prime plus 2, which we can factor as 2k prime in parentheses plus 1. So let's compile. And then, hence, n plus 1 is in the first set, and using k equals k prime plus 1. This suffices since this is the left side of the disjunction. Okay, let's make these, I really wish I had, well, let's make it look good for now. Maybe I'll fix it later. So I'll add a, I think it's called a baseline skip. Let's see how that looks. It's not nothing, so we'll just go with that. So I'll bold that, and then I'll do another baseline skip. I could have also just added a new line. Okay. So this completes the proof of the second claim. Maybe I should actually say why this proves it for the first claim. So using k equals 0, we see zeros in S. Okay. So I'll just do another baseline skip, get a little space, and hence S is an inductive set. Okay, well that's a proof. More wordy than it strictly needs to be, but you know, it's better to show you more words than fewer. That's what I figure. So long as they're not irrelevant words. Okay, now problem 3. Let's create a new environment, solution. I guess I poisoned it by accidentally creating a solutions before. Where am I? Right. Guess that got indented weird. Yeah, let's get this indentation better. And let's also create the solution there, just to get us started. Compile. Okay, so the thing that we're going to prove by induction is the statement P of n being that's a little LaTeX trick. Let's see if the spacing looks good. Yeah, okay. I just wanted that little space on both sides of the equal sign. Okay, the statement is 0 squared plus 1 squared plus dots plus n squared equals n times 2n plus 1 times n plus 1 over 6. So the first part, I guess I'll use a description environment for a base case and an inductive step. And the base case is P of 0 is that 0 squared is equal to 0 times 2, 0 plus 1, 0 plus 1 over 6. And both sides reduce to 0, and 0 equals 0. That's that. So the inductive step is for all n in the natural numbers, P of n implies P of n plus 1. So suppose n is a natural number and P of n is true, which is to say that this is an equality. And for the sake, well, let's set this off as a separate equation. Okay, so what we want to show is that when we substitute n plus 1n, that we get a true statement too. Okay, so did I just say this really weird? Let's see, what we'll show by induction is, okay, what I want to say is this, the statement we'll use for the induction is P of n. Okay, so we've done the base case. and the inductive step. So for all n, Pn implies Pn plus 1. Suppose n in P of n, which is to say that, and what we want to show is this. I guess since we're setting it off, we may as well use a fraction to hopefully make it look a little less of a mess. So I used the slash because I was doing it inline. It's a little bit better. And let's simplify that since it still is a mess and I think we want to simplify it anyway. So I'm going to use the align environment and then take this and just do the calculation right here. So let's see, we've got an n plus 1 at 2n plus 3 and an n plus 2, I think, which I will verify. Yeah, okay, the dot. All right, I have a meeting right now and I will be back. Okay, let's see, where were we? So we were proving this inductive step, and let's see. We calculated what we wanted to show. Let's recompile. And so we have this assumption. So really all we need to do is somehow use this assumption to prove the conclusion. And maybe the most obvious thing we could try is that this is a sum of the first n plus 1 numbers, so we should be able to reassociate. Let's see, so hence, let's include n squared in there. And then we can replace that with the conclusion of the hypothesis. Let's see where we are. Okay, so I took what we wanted to show's left-hand side and substituted in the right-hand side. Great. Now it's just a lot of algebra. And I guess we have to factor in stuff like that. So let's start by bringing it together. Okay, so let's add 6 times, no, I thought I had in my, oh, there it is. Okay, there's an n plus 1, and there's going to be an n plus 1, so may as well try factoring that out. So let's pull that n plus 1 out. So now, let's see if this compiles. Okay, so to get the left-hand side, we need to refactor this somehow into this expression. Not sure if there is a clever thing we can do, so let's not be clever, and let's just multiply it out. Okay, so we've got 2n squared plus n plus 6n plus 1, and let's turn that into a plus 7n. Oh, and that's not good. Oh, right, that should be a 6. Okay, that one is now a 6. And this ought to factor into the right thing, so I'll just write it and then check after I compile. So let's see, 2n times n is 2n squared, 2n times 2 plus 3 times n is 4 plus 3 is 7, and 3 times 2 is 6. Okay, and so which is what we wanted to show. thus, by induction, because we've shown both of the cases, for all n in n, P of n is true, which is what we wanted to show. Cool. So that's part A. Okay, so let's just review. We showed that the sum of the first n squares, including 0 squared, is this fraction. So the next problem is, so recalling, okay, so divisibility. The problem defines it. M divides n, or m is divisible by n, if there's some integer k, or natural number k, such that n times k is m. So, okay, so using what we've seen in other lectures, that's n divides m. So we want to show that for all n, this polynomial is divisible by 6. So one way we could do this is just directly, using some algebraic manipulation like in this problem. However, this polynomial is the top of this right here. And one thing that we can see is, okay, so I'll just write out what we can get out of this. And why this is part B. By part A, for all n in n, we have that 6 times this quantity is this polynomial. And so, by definition of divisibility, and using this value for k, the sum of the squares, we have that this polynomial is divisible by 6. So this problem's a little weird with, the solution's a little weird with the quantifiers. So I'm going to repair this. And the problem is that, like, what's under the for all, what's not. So let's just say, suppose n in n is arbitrary, because we're trying to prove this divisibility thing. What we will show, and I'm just being more explicit than really necessary. Let's copy paste. What we'll show is this, and then remove this quantifier because we just have an n on hand. So I think that fixes it. Okay, so suppose n is arbitrary. What we will show is that that polynomial is divisible by 6. Part A, we have this by multiplying both sides by 6. And then using k being this expression, we have that that polynomial is divisible by 6. Okay, that's all this was supposed to be. It's fine if you happen to do a much more complicated proof. It's good experience with induction if you did. Anyway, that's that. Okay, using only low-level definitions and theorems about natural numbers given in lecture, including the 2 rules given for multiplication, prove in a similar style, that these 2 things are true. Okay, for this we need to refer to what the lecture was, so I'll be right back as I pull that up. Okay, I found it. So we had these 2 axioms and 4 theorems. So let's go back, let's look at the problem. So we wanted to show for all a times 1 is a. All right, we also need the definition of multiplication. And that was a times 0 is 0, and a times successor of b is ab plus a. Okay, so let's see, where are we? So let's create our solution. Now I'll just paste these all in everywhere while I'm at it. So here's this one and that one. Okay, so we're right here. I believe we can just do this all in one line, so to speak, but I'll do it as in a line. So suppose a and n, and what suffices is that a times 1 equals a. And so I think we can just use the definition of multiplication directly without needing any induction or anything, because these rules are sort of inducting on the second variable just in the definition. So, okay, so we have a times 1, which is by definition of 1, a times s of 0. And then a times s of 0, let's check, is a times s. Okay, so we multiply the first number by what's in the s, and then we add the first number. So multiply by what's in the s, and then we add the first number. And I'll add a quad. I'll give the reason, and this is d. See, should I clarify what that d means? Yeah, I'll just say that. Let's see how that looks. And also, I'll say that this is by definition of 1. Oh, that's a little funky. Instead of a quad space, I'll make use of how the align environment works and get those to line up. Okay, so a times 0, that is property C, it's 0. Then 0 plus a, that was up here, that's theorem 1. That gives us a. Oh, theorem 1. I'll just put a period there and call that done, because we showed what we needed to show. Because it just feels silly saying any more than that. Okay, so for the next problem, I'm just going to assume that we don't need any fancy tricks. So let's suppose a is an a, and we will show 1a equals a. And by fancy tricks, I mean changing what the statement is at all. So this is probably a safe start. And so now, all we know about multiplication is what happens if the second thing is 0 or a successor. So we probably need to do induction to make this work, so let's just do it by induction. Maybe I didn't want to write it like this to be able to do induction. So we're going to prove a for all statement. So we will show by induction on a that 1a equals a. Okay, so let's set up the cases. We've got the base case and the inductive step. Because remember, the statement of induction as a theorem is that given that the statement's true for 0 and also when it's, well, when the inductive step is true, then it's true. And it's just convenient to have this like framework for applying that theorem to help the reader and you. Okay, so the base case is that when we substitute 0 in for a, we get 0. And then the inductive step is for all n in n. And I'm going to use a different letter than a just to, I guess, what do they call it in some programming languages? Hygiene. This is scope hygiene, just to have a different variable so we don't confuse things. So for all n, we want to show that if 1n equals n, then 1 times successor of n equals successor of n. That is what we want to show. And maybe this is a better way to format it. It's always good to think about new ways. Yeah, I think that seems clear, though I don't... Oh, what's up here doing there? Okay. So 1 times 0 equals 0. That is just axiom C. This is axiom C, and that's it. Inductive step. I think we can pull this off in just some equational reasoning. So we want to show that one successor of n, is stuff, and then eventually get s of n. Okay, that's what we want to show. We still have to fill in the details. So let's take a look at the definition again. So we have, okay, again, so 1 times successor of n is what we have, and so that should be 1 times n plus 1. 1 times n. It's a little weird seeing 1n with that. Like, 1 is never a coefficient, but oh well. Okay, so our reason is by multiplication axiom D. And now we need another thing to get to where we're going, because we're not at Sn yet. So 1n. Oh, right, I didn't actually set things up. So we're only trying to show this for all statement, but to show a for all, you have to invoke the thing that you want to, like, invoke the thing. So suppose n is in n, and also we're trying to prove a conditional. So let's assume its hypothesis. Suppose 1 is in n and 1n equals n. And what we want to show is that 1Sn equals Sn. Okay, so we have this hypothesis, which is 1n is n, so that we probably should just use it. We're almost there. All we need to do now is connect n plus 1 up to s of n. And that's true by definition of add, I believe. So, but first to use that, let's write 1 as s of 0. We're not going to leave any step out. So by definition of 1, okay, so n of s0 can be written by pulling the s out according to definition or axiom B. Yeah, by addition axiom B. And then s of n plus 0, so n plus 0 is n by axiom A. So we don't need another step because we already have the last thing. So by addition axiom A. Okay, so we showed what we set out to show. The inductive step is done. And now we can just say that we proved it. Thus, by induction, or this completes the induction, and that signals to the reader that what we will show by induction has indeed been shown by induction. Okay, so that is 4, going all the way down. Cool. Oh, maybe I should take that recall and where do I put that? Well, I'll just delete the recall part because that's in the original homework. Okay, now for the last problem. So we want to show that the binomial coefficient satisfies this property and also satisfies, or has, let's see, it's actually an integer because it's not obvious from the definition, from this definition that it's an integer. There's a combinatorial proof for this that I guess is out of scope for this class, and that is that this is supposed to be n choose k. It's the number of ways of choosing k things from n things with reordering, and they're all, yeah, and like it's just a count, so of course it's a natural number. And then you can show that this is true about it. And then so therefore this is a natural number. But let's do this in this algebraic way. And okay, so let's assume our hypotheses. Let n and k be in the natural numbers such that, well, I've been using suppose. A lot of authors use let to mean both supposing something and letting something have a particular definition. But I like using suppose to mean that something's been handed to you that's arbitrary and you're not defining it. Okay, so we have these numbers, and now we have, and we'll just calculate equationally. Right, so that's the left side, and we want to get to this right side. Oh wow, something went wrong with my editor that you can't see, it's just a bunch of spaces. Okay, so we need to fill in this gap. And what I think would be the right way to do this, partly because I've done this on paper once, but when I was creating the homework, but also I'm not sure how else you do it other than substituting in the definitions. So okay, so I plugged it in with k plus 1. Oh, that should be k plus 1. And then also down here, let's plug in the definition. So n plus 1, k plus 1, and k plus 1. Okay, so now we have this gap. I'm just doing a once over to make sure that nothing went wrong. Looks good. What I'm expecting will be useful is using the fact that k plus 1 factorial is k plus 1 times k factorial. So let's modify on both sides of this. We're going to work inwards to try to get them to meet. Let's do the same thing with n plus 1 factorial. So n plus 1 factorial is n plus 1 times n factorial. And we've got k plus 1 times k factorial. And I'm also, let's see, not sure to do this thing yet, but I'll just distribute that minus sign. Wait, why is there an extra? Oh, right, I have to delete the parenthesis. And then k factorial, and I'll distribute in a similar way. Delete the parenthesis. Oh, oops, I didn't mean to edit that one in place. That's fine. My editor lets me undo in a region. I'm a little too far. Okay, there we are. Okay, so is this a good transformation so far? Well, it's valid. Who knows if it's good yet? It's only good if we meet in the middle. Okay, so we've got n minus k minus 1. So it makes me think that I should have also modified this n minus k. Oh, I'm making sure. If n equals k, isn't this 0? I mean minus 1? That's not good. Oh wow, that's a little case analysis that we have to do. Yeah, because if n equals k, that's minus 1 factorial. So there's a little trick here in mathematical writing, and that's what we, just to say what we mean by minus 1 factorial. Oh, I see. For this to be valid at all, we need k plus 1 to be less than or equal to n. That's tricky. I did have that in mind when I was writing this, but I completely forgot. Okay. Okay, that is how we'll fix that problem. So k plus 1 is less than or equal to n. So we are allowed to do this thing, and it's just 0 factorial if, because k is not allowed to be n. When, so it's when k plus 1 is n. That's the lowest it can go. Okay, with that sorted out, okay, so I want to get the n minus k out of there. So, so we've agreed that n is bigger than k plus, or it's at least as large as k plus 1. So we can subtract an additional 1. Oops, that's a minus 1. Okay. So now here's what we will do. We see that both of them have a k factorial, and there's a k factorial there. And everything in sight has an n factorial on top. So, without thinking too far ahead, it seems reasonable to factor out the n factorial and the k factorial from the bottom. Okay, so I factored out the n factorial and the k factorial, and the n factorial and the k factorial. Okay, so that's been factored out. Oh, and also the n minus k minus 1 factorial. I should have noticed that. Okay. And may as well remove the parentheses while we're here. Makes it look a little nicer. Now I suspect all we really have to do is find some common factors, though I'm a little bit weirded out by this. because it doesn't look like it's gonna, oh, no, I think it's fine. Okay, so let's copy this, get some common factors. So we get k plus 1 and n minus k. And the k's cancel out. That's nice. And let's commute. Okay, so the tops are correct. And we've got the k factorial. And we've got the k plus 1. Where'd the n minus k go? So I made a mistake somewhere, obviously. It's time to just go through and read and see what went wrong. Or maybe it's right and I'm just not seeing it. Okay, well, let's check backwards first, because there's less going on. So we've got n plus 1 factorial, k plus 1 factorial, n minus k plus 1 factorial. So we get n minus k minus 1, and a k plus 1 factorial, k plus 1 times k factorial, and n plus 1 n factorial. So far, so good there. And up here, let's see, so that is n choose k, and that is n choose k plus 1. And then we had n factorial, k factorial, n minus k, n minus k minus 1 factorial, k plus 1 k factorial, n minus k minus 1 factorial. Okay, so then we factored out the n factorial, so we have 1s on top. And then we have k factorial on the bottom of both, so we factored that out. Wait, nope, still don't see. Okay, so then we have n minus k minus 1 factorial for both. Pull that out. Okay, so then each of these have 3 things. There's 2 things here and then 1 thing there and there, so that adds up to 3 for each. And so then we combine these together to get k plus 1 plus n minus k over their product. Well, then the k's cancel out, so we're left with n plus 1 on top, and this has not changed the whole time, which is good. So the top is correct, k factorial is correct, the k plus 1 is correct, but then I don't know what's going on here. It's usually nice having a whole classroom of students around to help debug something like this. I did it on paper. Let's make sure I'm proving the right thing. That's another good thing to check. Okay. I am, at least trying to prove the right thing. Because the problem is, what's popping out on the bottom is just a plain old n minus k factorial. And that is not what we want. Oh. It is what we want. I just am not able to do the right thing. Okay. Right. Okay, n plus 1. That is what should have been there. And then the 1s cancel out. And then these are equal. So just to make it clear why they're equal, I will combine this all together. partly. Okay, so I recombined the fractions together, and then brought the k plus 1 to the front, and the k factorial, then the n minus k, and then the n minus k minus 1 factorial. And then reordered. Wait, what did I do? What line am I on? Oh, okay, yeah, then that's the next line. And then that's the next line, and that's it. Great. Well, that was a little frustrating, but it all worked out. I'll blame having to explain everything as I'm doing it. It's a good exercise, because there's like the speech part of your brain which conflicts with the thinking part, or so I'm claiming, at least. So let's prove using induction that if we have two natural numbers with k is less than or equal to n, then n choose k as a natural number. This is actually exactly like the problem from before. This one about divisibility. So let's see. Yeah, okay, so suppose n and k are in the natural numbers. Oh, okay, let's see. What I want to, okay, the statement, this is actually by induction, and so the idea is that if we can show that both of these are natural numbers in the sum, then the sum is of course a natural number. So therefore, this is so we just need to inductively show that for every n, n choose k as a natural number for any k. And there is another way to do this, which is by induction just directly. And that's a good exercise in induction, but we already did all this work with all these manipulations, so better not redo it. So here's our statement that we're going to induct on. So the statement we will use for induction is p of n being for all k in the natural numbers. If k is less than or equal to n, then binomial coefficient nk is a natural number. I'm just stating that because there are two variables involved and what are we inducting on and all that. But we need to make sure that k is allowed to be anything for our induction hypothesis. So let us set up our base case and our induction step. And the base case is p of 0, and like usual, the inductive step is for all n in n, if p of n, then p of n plus 1, which I'm just writing explicitly there, like that. So p of 0, this is that, so what we will show is that for all k in n, if k is less than or equal to 0, then the binomial coefficient of that, where n is 0, is a natural number. So suppose k is a natural number with k less than or equal to 0. Then what we have, and maybe I should state that we're trying to, what we're going to show, but we've done this enough. It's sort of just, it's usually left unsaid. So one of the consequences of k being less than or equal to 0 is that then k is 0. And so we see that binomial coefficient 0k equals the binomial coefficient 0, 0, which is, by definition, I'll use a text fraction just so it doesn't make the, because these are display fractions and text fractions are for inline text. So this is 0 factorial over k factorial, this is n minus k factorial, which is 1 over 1 c dot 1, which is 1, which is an, let's see, I said a natural number, which is a natural number. Yeah, see, so that's what a t-frac does. It's small. I'll just show you what it would happen if I didn't do that. Oh, really? Okay, I didn't need to do that. I guess it's already inline style, so I'll just go back to frac. Sometimes I use this for fractions and matrices to make them smaller. Okay, so the base case is done, assuming I did it right. Okay, so suppose n is a natural number and p of n for all k less than or equal to n, then if k is less than then maybe that's a little confusing being written like that, for all k in n, because it might not be, it's not clear it's a natural number if you just write k is less than or equal to n. For all k in n, if k is less than or equal to n, then binomial coefficient nk is a natural number as our inductive hypothesis. What we will show is that for all k in n, I'll write it as k prime for some, so it's clear that these are different for all statements. If k prime is less than or equal to n plus 1, then binomial coefficient n plus 1 k prime is a natural number. Okay. So we have that, oh, it looks like there should be two cases then. Okay, so we got n plus 1 choose k prime, and what we showed before is n plus 1 k plus 1 has this formula. So I guess we should do this by cases on k prime, depending on whether k prime is 0 or not. But first, because we're trying to show a for all if, let's suppose k prime is an n and k prime is less than or equal to n plus 1, and we'll do cases. I wonder if this will render right. We'll see. So case 1 and case 2. Let's check the rendering. Okay, that looks good to me. I didn't, just wanted to make sure I indented nicely. So case 1 is k prime equals 0, and case 2 is k prime is bigger than, well, it's a successor. So maybe I'll write there is some k double prime such that k prime equals k double prime plus 1. So those are the two cases. In this case, I think this should be easy because what do we see? Let's calculate what this binomial coefficient is. So that's binomial coefficient with 0 plugged in, which is, now let's see if this all works on one line instead of doing multiple lines like before. So no double backslash. This is frac n plus 1 factorial, 0 factorial for k, and then n minus k would be n plus 1 minus 0 factorial. And that's 1, which is in a natural number. Last I checked. Oh yeah, now I can show you what t-frac would look like, which won't look good here, but yep, text fraction. So, okay, case 2, it's a successor. Let's set up in a line, and what we have so far, okay, so case 2, there's some k double prime such that k prime is k double prime plus 1, so we substituted it in. And then we use the theorem that we proved in part A. So by part A, that's the part, yep, because this is part B, that this is a sum of two binomial coefficients, which I'll just copy them in, remove the plus 1. I think it's this. And let's check. So n plus 1 goes to n, and then k plus 1 goes to k and k plus 1, n plus 1 to n, and k double prime plus 1 goes to k double prime and k double prime plus 1. Okay, so now we need to apply the induction hypothesis correctly. So we were supposing that for n and all k that are less than or equal to it, that n choose k as a natural number. So since k double prime is equal to k prime minus 1, and k prime minus 1 is less than or equal to n plus 1 minus 1 equals n, oh wait, I copied the wrong part. Oh no, okay, so just need to see this compiled. Okay, so k double prime is k prime minus 1, which is less than or equal to, so k prime is less than or equal to n plus 1, and we subtract 1, and that's n. And so we can apply the inductive hypothesis. So there's something I'm a bit concerned about, because I'm not sure why we're going to be able to apply this one. Maybe I set up the wrong induction, but okay, so k Wait, did I write the wrong induction hypothesis? Okay, just to read it more carefully. So we want to show that if we have a natural number n, and p of n is true, which is k, for whenever k is a natural number that's less than or equal to n, then n choose k as a natural number. That's our hypothesis, and we want to show that this is true for n plus 1, which is that whenever k prime is a natural number that's less than or equal to n plus 1, then n plus 1 choose k prime as a natural number. That is indeed what we want to show. So we suppose that k prime is a natural number and k prime is less than or equal to n plus 1. So case 2 is that k double prime is the predecessor to k prime, because k prime is not 0 in this case. And by part A, let's see, okay, so n plus 1 choose k prime, substituting in k prime, so n plus 1 choose k double prime plus 1. Part A gives us this. And so for this to be an integer by the hypothesis, we need k double prime plus 1 to be less than or equal to n. And I don't know, I was confused about this. Okay, I'll write this differently. Since k prime is less than or equal to n plus 1, then k double prime plus 1 is less than or equal to n plus 1. So k double prime is less than or equal to n. No, I'm still confused, because I want k double prime plus 1 to be less than or equal to n. Do I also have to have another case, which is, I guess I have to have another case. I didn't realize this. Another case for when k double prime plus 1 equals n, which is definitely a possibility. Interesting. Well, let's add it to the cases. Case 2, k prime equals n plus 1. So, okay, in that case, it's basically the same as this, or I expect. I just have to modify things around. So, n plus 1, and now this would be n plus 1 factorial, and we have n plus 1 minus n plus 1, and so that's 1. Which one can calculate? I wonder if anyone wants to see this with the 0 there, but I'll just leave it as is. Okay, so case 2. I'll state it differently now, which is that 0 is less than k prime is less than n plus 1. So now what we have is that there is some k double prime in n such that k prime equals k double prime plus 1. And what do we know about it? Well, we know that since we're just subtracting 1 from k prime, that we have 0 is less than or equal to k double prime is less than or equal to 2. So I'll clarify that by saying we see. And I just don't like C into sentences right after each other, so okay, we have that. Okay, so by part A we have this, and okay, so now since k prime is less than or equal to n plus 1, well, do we need that anymore? Instead it's, we want, so k double prime, wait, why did I write 2? I meant n minus 1. I was subtracting 2, that's what was in my mind. Because it's an integer, if it's less than n plus 1, that means it's less than or equal to n, and so it's less than or equal to n minus 1 after subtracting 1. Okay, so since k double prime is less than or equal to n minus 1, which is less than or equal to n, we can apply the induction hypothesis to say that binom n k double prime is a natural number, and since k double prime plus 1 is less than or equal to n minus 1 plus 1, which is less than or equal to n, we can apply the induction hypothesis to say that binom n k double prime plus 1 is a natural number. Okay, that seems good to me. Well, I should say, hence, binom n plus 1 k prime is a natural number since it is the sum of two natural numbers. So I guess if you're somebody who proved this by induction from scratch, from the by using for the divisibility version instead, you did not see this 3 case thing. Oh, I should write case 3. Well, anyway, that was a little exciting. Let's complete this up now. So we proved the induction step, and so what we can say at the end is this completes the induction. And let's see, how did we start it up? That's the statement. Okay. We didn't say by induction blah blah blah. We were just saying the statement we will use. Okay, so by induction, using Pn, induction on n, using Pn, we therefore how do I want to say this? Maybe for all n in n, p of n is true, which is what we wanted to show. Okay, let's give this a once over now. Okay, so we had this set S. We wanted it to be non-empty. And we showed that 3 is the least element just by noting that 0, 1, and 2 were not in it, just by looking at them. Okay, so in inductive set, we wanted to show it's inductive by the definition. So we showed 0 is in it just because when k is 0, it's in the left-hand side of the union. And also, whenever n is in it, so it can be represented either as an even or odd number, then adding 1, it's an odd or even number. So a lot to say for that. Problem 3. So we wanted to show that this is true using induction. So we showed it's true for 0, and then by some algebra, we showed it's true for n plus 1 from n. Then for the divisibility problem, we just had to multiply both sides by 6, and that was the definition of divisibility. Nice. So, okay, then there's problem 4, which was showing this very basic property of multiplication, and it was some sequence of definitions and axioms and theorems from the lecture. And we did the same. Okay, so then there's the binomial coefficient, which, because I messed up substituting right here, I got stuck for a while, but thankfully it all worked itself out. It had to have, because this is a well-known identity. And then there was proving that there's this divisibility property. And we used the work from the previous problem to then show that we can apply, or show that the binomial coefficient, at least when all the numbers are right, is the sum of two integers, so therefore it's an integer. But it turned out we had to handle the lower and upper bounds for k specially, which is interesting. Well, it's probably good. If there are any errors, let me know. I'll update this. And anyway, if you stuck to the end, hopefully you got something out of this. Let me know if you did. And let me know if you want to see more of these. And anyway, see you next time.